So now we're going to look at why would we want to convert from log form to exponential form? What kind of benefit would that give us? So this often helps us if we're ever trying to evaluate logarithms. We have a little process that we follow. For example, in this idea, part A, we're looking at log base 3 of 81. And we actually want to know, is there a nicer number or a nicer way to say this? So if we were trying to get our TI out, you'll notice that the base of this log is not a 10 and it's not an E. So you can't really directly evaluate it unless you know a trick, which we will show you a little bit later. But in the meanwhile, it's a little faster. If you don't know this value of the logarithm, you can set it equal to a variable. And we say X is our favorite variable, so we will do that. And now that you have a logarithmic form or equation, you can convert this to exponential form. So if you remember some of the shortcuts, I'm going to convert. And when I convert, it's the base, that's 3 to the other side, so that's 3 to the x, is equal to the argument, which is 81. So now we have the exponential form of log base 3 of 81 equals x. And this is the case where now we do a little game of comparing powers of numbers. So usually what I do is I start off with looking at the smaller number, which is 3. And then I just ask myself, can I rewrite 81 as a power of 3? As 3 to some number. And maybe I'll make it a box so that I can figure out my question mark. There we go. So, you know, you get really good at this after you do a lot of examples, but when I start, no big deal. I just start dealing with powers of 3. I say, okay, 3 to the power of 1, that is 3. That is not 81, so keep going. 3 squared, that is 9. Keep going. 3 to the third, that is 27. 3 times 3 times 3. And I keep going. We're not quite at 81. 3 to the fourth. I may not know that off the top of my head, but I know that it's 3 to the third times 3, so 27 times 3. Might get your calculator out if you'd like. I'll just go the roots. 7 times 3 is 21. 2 times 3 is 6, and we have our 81. So you don't always have to know the answer right away, but you know, test it out for yourself. So that is true. The answer, we can rewrite 81 as 3 to some power. 81 is actually 3 to the fourth. So all I do is replace the 81. And at this stage, you now have 3 to the x equals 3 to the fourth. And you have a statement equating the bases. If the bases are the same, which they are, we now automatically can set the exponents equal. In this case, it's x equal to 4, and drop the bases. You don't really have to write set if we don't want to. This is a nice little statement. So we do know now that x is equal to 4, and if x was equal to log base 3 of 81, a better way to say log base 3 of 81 would just be to say, hey, it's 4. You know, I'd rather say I have $4 or I have log base 3 of $81. So that's kind of a nice way we can find actual values of these logarithms without having to pull our calculator out to approximate. You know, sometimes the numbers get huge, and I get it. We can use our calculators to help us out with powers. But if you have a pretty good idea of how powers work, like powers of 2, powers of 3, powers of 4, maybe some powers of 5, and powers of 10, you have a pretty good chance of getting through a lot of these problems without needing a calculator. So let's just kind of keep going and take this same technique for part B and part C. Same idea. If I don't know log base 4 of 4, I'm going to set it equal to a variable. X is my favorite. I'll then rewrite it. 4 to the power of x equals the argument, equals the 4. So now when you look at your exponential form, you'll notice already that the bases are equal. You do see 4. You don't quite see an exponent on this single right-hand side, the 4, but we do know that it is a power of 1. So right away, you can set the exponents equal. And what that means is you're saying, hey, x equals 1. And drop the bases. It's kind of another idea of what it means to be an equality. So now that you know who the power of x is, or the logarithm is, x is 1, you can now rephrase this. Do I have log base 4 of $4 or do I have $1? It's a lot easier. So that's the answer to our evaluating the logarithm. Super nice, I like these. So let's keep going. Kind of an interesting one that we run into sometimes. And then these kind of translate, you'll see some properties along the way, maybe it's a future section. But again, I don't know log base 7 of 1 off the top of my head. So anytime I run into a situation like this, I'm going to set it equal to a variable. So if I set this equal to x, I'm going to rewrite 7 to the x power, 7 to the x equals the argument, which is 1. Now, when you start looking at the 7 versus the 1, you're going to look at it and say, well, you know, it's really hard to write 7 as a power of 1, but maybe we can write 1 as a power of 7. This is a little trickier because we do have to think a little bit backwards, but there is a property that allows us to rewrite the 1 as any power as long as the exponent is 0. So if you guys remember, 1 is the same thing as 7 to the 0 power, or any number to the 0. So kind of recall exponent rules. What do we have? Like n to the 0 power is always equal to 1. So it does not really matter what the n is as long as it's not 0. So 1 is rewritten as 7 to the 0. And that leaves us with 7 to the x equals 7 to the 0. So guess what? We set the exponents equal. We're going to get x equals 0. Drop the bases. So what does that mean? Log base 7 of 1. Instead of saying this, we would say 0. So that's the evaluation. So that one takes a little bit of time, but you'll start recognizing if it shows up a lot more. There's some properties that come into play there. Let's take a little bit more time. Do a couple of other ones that look a little bit scarier, but still doable if we know some log properties. Starting off with part A. I don't know if we were able to look at this in the section yet, but you see that you don't see the log, the log. But when you see ln, that's the log natural or natural log, it's a little reminder to us. Natural log, also known as ln, it does have a base. That's the e. That's Euler's number. So it's like 2.71 something, something, something. So what you can do is you can say, okay, well, I still know it's a log. Sometimes if you prefer, I don't know if you want to take this route. If you see natural log of x, for example, you could rewrite it as log base e of x if that's something that you are into. But most of us will start seeing it in ln form, so we assume that we just have a base of e. So sometimes you'll even see me write it in at the bottom. Squeeze that in there if you can. Sometimes you might have to blow it up a little bit to see it a little bit more, so I'll do that. Now, we still are dealing with a logarithm, so we're going to set it equal to our favorite variable, x, and we'll rewrite it in exponential form, just like we did with the other problems. So if we write an exponential form, that is e to the power of x is equal to the argument, which is e to the fifth. Now, it doesn't really matter what the e's are. The cool part is we see right away that they're equal. So we have equal bases. So at this point, we can set the exponents equal. So that means x equals 5. So if we were trying to figure out what is this value, natural log of e to the fifth is really just us saying the number 5. That's us evaluating the log. So that's a nice little property we'll see a little bit later, but you don't always have to memorize the properties if you understand how to work with these logarithms. Let's do one more fun one. Looks a little scary, but we can handle this. Again, right away you see logarithm, a number base, a number argument. First thing we'll do, set it equal to x. Now we'll take our time and we will rewrite it in exponential form. So base 0.1 to the x power is equal to the argument, which is 100. And this one, my friends, I feel it's a lot more trickier because we're not really thinking decimals at this point. But whenever I see 100, I'm thinking, okay, that's a beautiful power of 10. I do know that 100 is 10 square. And so I'm just toying around with this. You may kind of look at 0.1. You're saying, well, that's technically has to do with something like 10. I know it's a decimal. And 0.1 can be rewritten as a fraction that involves 10. 0.1 is the same thing as 1 over 10. So technically, it's still taken to the power of x. So now I'm kind of seeing the tens come into play. And it's okay if you don't see it right away. That's why I'm trying to show you an example so you get that experience. Tens are popular in this sense, so come back and refer to this a little bit later. But anyways, we're almost set. We kind of see that we have some equality with some of the bases happening, except for 1 over 10 is not on the same level as 10 squared. One's a fraction, one's a nice integer. So what I'm going to remember a little bit more is whenever I had a power in the denominator, and even though we might not be able to see it, technically the power of 10 that I see in the denominator is 10 to the power of 1. If I want to move that to the numerator, another law of exponent that comes back to haunt me a little bit, you guys remember, if you have a exponent in the denominator, you can switch levels in a sense. You can technically move that factor up to the top, but if you do that, what happens is that it changes the sign of the exponent. So that becomes x to the negative n. Another law coming back to haunt us. So if we take that same approach and we say, hey, that's 10 to the 1 in the denominator. If I want to move that to the top, what do I have? Is not 10 to the 1, it is now 10 to the negative 1. So that, my friends, is still taken to the x power. And we still have ourselves equal to 10 squared. And we are almost set. But we have a little bit more complication. We have an exponent expression taken to another power. So you guys remember another law? Anytime you had something that had an exponent and it was taken to another exponent, you would keep the base and multiply the two exponents. Same story goes with this one. So this 10 to the negative 1 taken to the x power is really just 10 to the negative 1x. And now we are on the same level. We have nice power of 10. Whoops, I was going to highlight that. There we go. Nice power of 10. Nice power of 10. Now that the bases are equal, we'll set the exponents equal. And if you solve this resulting equation, technically you're dividing both sides by negative 1, we get x equals negative 2. So what does that tell us? If you're going to say this in English, log base of 0.1 of 100 is really equal to just negative 2. That's our evaluation of the log. So that one was a little bit more involved than the ones we've been dealing with, but don't be afraid. Think outside the box. I like to show these examples so that it kind of reminds you of a few things from your past, that being some of the laws that we are working with, can definitely help us out when they get a little more complicated than the previous ones. So I hope this helps. I'll see you for the next example.